Welcome to a screencast on an introduction to intermolecular forces. When we were dealing with gases, the molecules of gas are far apart and the attractions between the molecules are very, very small. In fact, if we're dealing with an ideal gas, then the attractions between molecules are negligible. They're essentially non-existent, not significant enough for us to consider. But if we're dealing with a liquid or a solid, then the molecules are close together and the attractions between the molecules are now important or significant. They matter quite a bit, and in fact these attractions between molecules in a solid or liquid are what keep those molecules close together. So when we deal with a liquid or a solid, we need to take this into account. We need to consider the forces of attraction that act between the molecules of the substance we're interested in. And it turns out that lots of chemical properties, including the melting point or boiling point of a substance, what it's soluble in, protein structure, how DNA functions, viscosity of a liquid, all kinds of different properties can be understood via what are known as intermolecular forces. So let's take a look at these intermolecular forces, starting with example 1, which is a comparison of fluorine, F2, with hydrogen chloride, HCl. And here are representations of molecules of F2 and HCl. And F2 is a nonpolar molecule, two fluorine atoms bonded together. It has a molar mass of about 38 grams per mole, and its boiling point is negative 188 degrees Celsius, pretty low. HCl, hydrogen chloride, is a polar molecule with a fairly similar molar mass to fluorine. Its molar mass is 36.5 grams per mole compared to the 38 for fluorine, and its boiling point, while low, is quite a bit higher than the boiling point of fluorine. It's negative 85 degrees Celsius, about 100 degrees higher, 100 degrees Celsius higher than the boiling point of fluorine. And it turns out that hydrogen chloride has a higher boiling point than fluorine because HCl has what is known as dipole-dipole attractions. And here's what's going on. Here's a molecule of HCl, H bonded to Cl, and since chlorine is a more electronegative element than hydrogen, then the electrons that are shared between hydrogen and chlorine are unequally shared. They're drawn more towards the chlorine, so that side of the molecule becomes slightly negatively charged, and the hydrogen side becomes slightly positively charged. And if there's another HCl molecule nearby, then the negative end of one HCl is attracted to the positive end of another HCl, and that attraction, that attractive force between these two molecules is called a dipole-dipole force. It's one type of intermolecular force, and it is an attraction between a dipole in one molecule and a dipole in another, hence the name, dipole-dipole forces. And the generalization is the more polar a molecule is, the stronger its dipole-dipole attractions. In this case, HCl has a dipole and F2 doesn't, so of course HCl will have a much stronger dipole-dipole attraction, but if we had a molecule of a similar size with a bigger dipole, then it would have an even stronger attraction than HCl. Okay, second example, let's compare fluorine, F2, with its cousins in the halogen group, chlorine, Cl2, and bromine, Br2. And notice these are all diatomic molecules. They're all nonpolar, and the big difference is fluorine is about 38 grams per mole, chlorine is significantly larger, about 71 grams per mole, and bromine's about 160 grams per mole. And the boiling points of these substances are negative 188 degrees Celsius, negative 35 degrees Celsius, and positive 59 degrees Celsius. And we note that as the molecules get bigger, their boiling points increase. And so what we have here is that even though these molecules are nonpolar, they do have attractive forces. enough that they will form liquids and solids at various temperatures. They don't stay gas. And these attractive forces, which all molecules have, are called instantaneous dipole attractions, and technically it's instantaneous dipole attractions, and that's kind of cumbersome as a term. We often call these London dispersion forces. And what's going on here, let's compare or consider what's going on with fluorine. And if we look at the electrons in a fluorine molecule, the electrons may not necessarily be evenly distributed all the time. And if we look at, this is kind of an extreme example for purposes of explanation, but if we look at this molecule, we'll notice there's more electrons on the right side of the molecule than on the left at this particular instant. And what that means is the right side of the molecule is slightly negatively charged, and the left side of the molecule is slightly positively charged by comparison. And so we have temporarily, because of this sort of uneven distribution of electron density, we have a slight dipole called an instantaneous dipole pointing, in this case, to the right of this particular molecule. And that can either induce a dipole in a nearby molecule, or a nearby molecule could have its own instantaneous dipole. And then what happens is the negative end of one instantaneous dipole can attract the positive end of a nearby molecule with an instantaneous dipole. And we therefore have a second type of intermolecular force, which is an instantaneous dipole attraction, called a London dispersion force. So that's our second kind of intermolecular force. And the generalization about London dispersion forces, all molecules have them. They are the only type of force in nonpolar molecules, and the generalization is the larger the molecule, the more unevenly distributed its electrons can be. This is called polarizability. More on that later. And so larger molecules are more polarizable, which means that they can have larger instantaneous dipoles, which means they have stronger attractions between their molecules. And then our third example, let's consider once again the halogens, but now hydrogen halides. So HF, hydrogen fluoride, compared to HCl, hydrogen chloride, compared to HBr, hydrogen bromide. And HF is 20 grams per mole, HCl is 36 grams per mole, HBr is 81 grams per mole. All of these are polar, and they get increasingly large, going from HF to HCl to HBr. So we would expect increasing London dispersion forces going from HF to HCl to HBr. And if we look at the boiling points, it's plus 20 degrees Celsius for HF, negative 85 degrees Celsius for HCl, and negative 67 degrees Celsius for HBr. So the increase in boiling point due to size of molecule is true for HCl going to HBr, but even though HF is really small, it has a very high boiling point, kind of out of scale for what we might predict. And the reason is HF has a much, much higher boiling point than HCl or HBr because it has an intermolecular force called hydrogen bonding. And what's going on in hydrogen bonding is we have a hydrogen, hence the name hydrogen bonding, bonded to a very small highly electronegative element, and the three elements that can potentially have hydrogen bonding are if we have a molecule with H bonded to oxygen, H bonded to fluorine, or H bonded to nitrogen. So fluorine, nitrogen, and oxygen are the three very small, highly electronegative elements that can create hydrogen bonds. Here we have water, and what ends up happening is the oxygen side of water becomes slightly negatively charged. The hydrogen side becomes slightly positively charged. Those negatives and positive regions on nearby molecules attract strongly, and because the oxygen in this case is a very, very small, highly electronegative element, This gives us a very, very strong dipole in a small region, and so that's an extra specially strong type of attraction. So it's a subset of dipole-dipole attractions, but it's so strong it's given its own category, and it's called hydrogen bonding, and this is our third type of intermolecular force. And the generalization is that if we have molecules with a hydrogen that is bonded directly to a fluorine, an oxygen, or a nitrogen within that molecule, then those types of substances are capable of undergoing what's called hydrogen bonding. And then one last note is the bonding here is in quotations because these aren't true chemical bonds. These are really strong intermolecular forces represented by the dotted lines here, but they are not true chemical bonds, but chemists refer to them as hydrogen bonding nonetheless. So those are the three types of intermolecular forces: dipole-dipole attractions, London dispersion forces, and hydrogen bonding. And hopefully that's enough to get us started with our introduction to intermolecular forces.